Welcome to Nexus. If you're new here, this is your go-to place for everything instrumentation and control. Today, we're diving into one of the most fundamental components of process control systems, control valves. Control valves play a critical role in regulating flow, pressure, temperature, and level in industrial processes. Whether you are in oil and gas, power plants, or any other process industry, understanding how control valves work is essential to ensuring systems run smoothly and efficiently. In this video, we'll cover the basics, what control valves are, how they function, their types, and why they're so important in maintaining system stability and performance. By the end, you'll have a solid foundation in control valves, and you'll be ready to apply that knowledge in real-world scenarios. In this training, we will cover the below contents. 1. Introduction to control valve. 2. Control valve classification. 3. Control valve component. 4. Control valve sizing. 5. Code and standard. So, let's get started. Make sure to hit that subscribe button and ring the bell so you don't miss out on more insights into the world of instrumentation and control. What is the valve? A valve is a device that regulates the flow of fluids, either gases, fluidized solids, slurries or liquids, by opening, closing, or partially obstructing various passageways. What is a control valve? A control valve is a valve used to control fluid flow by varying the size of the flow passage as directed by a signal from a controller. This enables the direct control of flow rate and the consequential control of process quantities such as pressure, temperature, and liquid level. Most common applications of valves in the process industries are block valve. It is a manual-operated valve. These valves are usually fully opened or closed, although they can be used to regulate flow over short periods with a person adjusting the valve opening. And the next one is safety relief valve. Self-actuated, the difference between process and external pressures results in opening when appropriate. These are located where a high, low pressure in a closed process vessel or pipe could lead to an implosion. And the next one is on-off valves, usually operated by electric motor or air-operated or hydraulic-operated. These valves are normally used for isolating process equipment by ensuring that flows are not possible. They can be operated by a person in a centralized control room, who can respond quickly regardless of the distance to the valve. Throttling control valves, usually operated by pneumatic pressure. These valves are typically used for process control, where the desired flow rate is attained by changing the opening of the valve. Valves can broadly be classified into two categories. 1. Manually actuated valves. 2. Power-actuated valves. Power-actuated valves are further divided into positioning valves like control valves and regulators. Stop or block valves. Relief valves which protect equipment from overpressure. Now let's talk about control valves, which play a critical role in regulating flow. They are classified based on the motion type, a linear motion valves. These valves move in a straight line to control flow. They include globe valve, offers precise throttling. O-types, single-seated, double-seated, and split-bodied. Diaphragm valve, pinch or clam valve. Gate valve, includes knife gate and multi-orifice types. Rotary motion valves. These operate with a quarter-turn motion. Examples: plug valve, comes in cylindrical, tapered, and eccentric sphere types. Butterfly valve, includes swing-through, lined, and eccentric varieties. Ball valve, can be full, segmented, or V-notch types for control applications. Regulators are a special type of control valve that self-adjusts to maintain a set pressure level without external control signals. In real-world instrumentation, the selection of valves depends on factors like process fluid, required control accuracy, temperature and pressure conditions, maintenance accessibility. Understanding this classification helps you choose the right valve for the right job, which can boost process efficiency and safety. There are two basic types of control valves, rotary and linear. If the trim moves in a straight, vertical motion to open or close the valve, it's known as a linear valve. On the other hand, if the trim operates with a rotating or side-to-side motion, it's classified as a rotary valve. Linear motion control valves commonly have globe, gate, diaphragm, or pinch type closures. Rotary motion valves have ball, butterfly, or plug closures. Each type of valve has its special generic features, which may, in a given application, be either an advantage or a disadvantage. Linear valves are tortuous flow path, low recovery, can throttle small flow rates, offers variety of special trim designs, suited to high-pressure applications, usually flanged or threaded, separable bonnet. Rotary valve features streamlined flow path, high recovery, more capacity, less packing wear, can handle slurry and abrasives, flangeless, integral bonnet, high rangeability. Globe valves. When it comes to precise flow regulation and frequent operation, this type of valve stands out. It's best suited for linear and equal percentage control characteristics, making it ideal for applications where smooth, accurate throttling is essential. Typical uses include throttling services and systems that require continuous or frequent modulation. You'll find these valves effectively handling liquids, vapors, gases, corrosive substances, and even slurries, showcasing their versatility in a wide range of industries. Some of the key advantages of this valve include efficient throttling. It offers excellent flow control performance. Accurate flow regulation, which is crucial for tight process control. The option to be configured in multiple port designs, allowing flexibility in complex systems. And a wide control range, which makes it suitable for both small and large flow variations. However, like any equipment, it comes with a few disadvantages. It causes a high pressure drop, especially when fully open. And it tends to be more expensive compared to other types of valves, such as rotary or on-off types. Despite these limitations, its performance benefits often justify its use in critical process control environments. Based on the flow paths, the globe valves can be classified as single-seated globe valve, double-seated globe valve, angle valve, three-way valve, cage. We will have a separate video on these valves since it requires more time to explain. Now let's take a look at the gate valve, a valve designed primarily for on-off control rather than throttling. Gate valves are best suited for quick opening applications where the valve is either fully open or fully closed. They're typically used in systems that require infrequent operation and minimal fluid trapping in the line. Applications include oil and gas, air, slurries and heavy liquids, steam, non-condensing gases, and even corrosive liquids. Gate valves offer several advantages. 1. They provide high flow capacity due to minimal obstruction when fully open. 2. They ensure a tight shutoff, making them suitable for isolation. 3. They're generally low in cost, especially in larger sizes. 4. And they introduce very little resistance to flow, which reduces energy losses in the system. However, they're not without drawbacks. 1. Gate valves offer poor flow control, making them unsuitable for precise modulation. 2. They tend to cavitate at low pressure drops, which can damage the valve when piping. 3. And most importantly, they should not be used for throttling. Doing so can cause seat and disc erosion. In short, gate valves are ideal for isolation but not for regulation. Understanding this distinction is key to using them effectively in your system. Rising stem gate valve and knife gate valve are the other types of the gate valves. Next, let's talk about ball valves, a widely used valve type known for its quick operation and compact design. Ball valves are best suited for quick opening applications, but they also offer a somewhat linear response in certain limited throttling scenarios. They're typically used in systems where rapid shutoff or opening is needed. They are recommended for 1. Fully open or fully closed operation. 2. Occasional limited throttling. 3. Handling high temperature fluids. Common applications include most liquid systems, high temperature services, slurry handling, thanks to their robust design and minimal fluid entrapment. When it comes to advantages, ball valves stand out for 1. Their low cost, especially in standard sizes. 2. High flow capacity with minimal pressure drop. 3. Low leakage and low maintenance requirements. 4. And a tight seal with low operating torque, making them easy to actuate. But there are limitations you should be aware of. 1. They have poor throttling characteristics, meaning they're not ideal for precise flow control. 2. They are prone to cavitation, especially in low pressure drop or flashing conditions. In summary, ball valves are excellent for isolation and rapid switching applications, but they're not the best choice for fine-tuned control. Three-way ball valve, segmented ball valve and V-notched ball valve are the other types of ball valves based on the different applications. Let's move on to butterfly valves, known for their compact design and versatility in both isolation and control applications. Butterfly valves are best suited for linear and equal percentage flow characteristics, which makes them a solid choice for both on, off and modulating control. They're highly recommended for 1. Fully open or closed operations, as well as throttling services. 2. Frequent operation due to their fast actuation. 3. Systems where minimal fluid retention is important. Common applications include liquids and gases, slurries, fluids containing suspended solids, thanks to their streamlined disc design. Their advantages are noteworthy. 1. Low cost and maintenance, making them ideal for budget-conscious operations. 2. High flow capacity, allowing large volumes to pass through with ease. 3. Good flow control across a wide range of applications. 4. And a low pressure drop, which improves energy efficiency in the system. However, there are a couple of disadvantages to keep in mind. 1. They require higher torque for precise control, especially under pressure. 2. And they are prone to cavitation, particularly at lower flow rates. In essence, butterfly valves strike a good balance between performance, cost, and control, especially in medium pressure, high flow applications. Let's now explore some specialized valve types that are critical in specific process applications. These valves might not be as common as globe or ball valves, but they play a unique role in various systems. Let's look at each one with visuals for better understanding. 1. Diaphragm valve. First up is the diaphragm valve. This valve uses a flexible diaphragm that presses down onto a weir or saddle to regulate or stop flow. It's especially useful for handling corrosive or slurry-type fluids because the fluid never touches the internal moving parts. It's simple, clean, and often used in pharmaceutical and food-grade applications. 2. Pinch or clam valve. Next, we have the pinch valve, also called a clam valve. It operates by pinching a flexible tube or liner inside the valve body. When the compressor mechanism is tightened, it pinches the liner and blocks the flow. It's perfect for highly abrasive or fibrous fluids, just like squeezing a hose shut. 3. Plug valve. Then comes the plug valve, a simple, quarter-turn valve with a cylindrical or tapered plug that rotates to control flow. These are compact and reliable for on-off operations. Some types, like the lubricated plug valve, are used in high-pressure applications. Notice how the internal plug rotates to align or block the passage. 4. Eccentric plug valve. And here's the eccentric plug valve, an advanced version of the plug valve designed for better sealing and throttling performance. The plug moves in an eccentric path, which minimizes seat wear and allows it to handle slurry and semi-solid fluids more effectively. Each of these valves, diaphragm, pinch, plug, and eccentric plug, serves a unique function. The choice depends on the nature of the fluid, system requirements, and desired control accuracy. Mastering these will help you design or troubleshoot systems more effectively. Let's now look at one of the most critical aspects of control valve design, flow characteristics. Control valve plugs aren't just shaped randomly. They're carefully engineered based on how we want the valve to respond to changes in the control signal. And that's where inherent flow characteristics come in equal percentage, linear and quick opening. Understanding flow characteristics is key to select the right control valve for your process. Let's look at the four most common types: equal percentage, linear, quick opening, and modified parabolic. 1. Equal percentage. In this characteristic, equal increments of valve travel produce equal percentage changes in flow. It's ideal for applications with large pressure drop variations, temperature or pressure control loops, processes where the valve handles only a small portion of the total system pressure drop. 2. Linear. Here, the valve travel is directly proportional to flow. That means a 10% stroke change results in a 10% flow change. Best suited for liquid level or flow control loops. Steady state systems where the pressure drop across the valve remains relatively constant. 3. Quick opening. A small change in valve stroke results in a large increase in flow. This is perfect for frequent on-off operations, safety systems or cooling systems where instant high flow is required. 4. Modified parabolic. This curve is a blend. It's midway between linear and equal percentage. It offers fine throttling control at low flow and approximately linear performance at higher flow capacities. Choosing the correct flow characteristic ensures your control valve responds appropriately to process changes, enhancing stability, efficiency, and safety. Flow characteristics is divided into two key types. 1. Inherent flow characteristic. This curve is defined under constant pressure drop conditions across the valve. It represents the ideal flow behavior of the valve, without considering any piping, fittings, or system dynamics. 2. Installed flow characteristic. But in the real world, valves are installed in systems with pumps, pipes, elbows, and other process equipment. As a result, the pressure drop across the valve changes as the valve opens or closes. When we plot the actual flow in the system against valve opening under these varying conditions, the result is known as the installed flow characteristic. Understanding the difference between these two characteristics is essential. While the inherent curve helps in selecting the right valve for a given application, the installed curve helps you predict and control real-world performance. Seat leakage classifications. In the world of control valves, you might often hear the term bubble tight, but let's clear up a common misconception. There's no such thing as a truly bubble tight control valve. Control valves are primarily designed to throttle, to regulate flow, not necessarily to provide zero leakage shutoff. However, in real-world systems, they're often expected to do both, control the flow and shut off when needed. A valve's shutoff capability depends on multiple factors. The type of valve, for example, a double-seated valve generally offers poor shutoff performance. The seat and plug material, actuator thrust, pressure drop across the valve, and even the type of fluid in service. To help standardize expectations, ANSI FCI 7022 defines 6 leakage classes. But in most industrial applications, you'll typically be concerned with just 2. 1. Class 4, also known as metal-to-metal shutoff. This applies to valves where both the plug and the seat are made of metal. A small amount of leakage is expected due to the lack of soft sealing. 2. Class 6, this is the soft seat classification. In these valves, either the plug, the seat, or both are made of a composite material, like Teflon. These valves offer superior shutoff performance and are used when tight sealing is a priority. So remember, while perfect shutoff isn't guaranteed in control valves, understanding seat leakage classes helps you choose the right valve for the right job. Now let's take a look at the 6 ANSI FCI leakage classifications for control valves, a critical factor when you are selecting valves based on shutoff performance. Class 1. This is more of a default category. Valves in Class 1 are not tested for leakage in the factory, but are built to the same design standards as Class 2, 3, and IV. Class 2. These are typically double-potted or balanced single-potted valves with metal piston ring seals and metal-to-metal seats. The test fluid is air or water at 45 to 60 psi, and leakage is limited to 0.5% of the valve's rated full open capacity. Class 3. Also intended for similar valve types as Class 2, but with tighter leakage limits. Here, the allowable leakage is just 0.1% of rated valve capacity. Class 4. Designed for single-port or balanced single-port valves with extra tight piston seals and metal-to-metal seats. This is the first class used for true shutoff performance, allowing 0.01% leakage of rated capacity. It's the go-to for many industrial control applications. Class 5. This class takes it a step further. Also intended for valves similar to Class 4, but tested using water at 100 psi or operating pressure. Leakage is limited to 5 by 10 to the power of 4 milliliters per minute per inch of orifice diameter per side differential, a very tight standard. Class 6. Reserved for resilient seated valves, where either the plug, seat, or both are made of soft materials like Teflon. Tested using air or nitrogen, with a pressure of 50 psi or less, Class 6 valves are ideal for applications requiring bubble-tight shutoff. Knowing these classes helps you select a valve that matches your process needs, whether you need precise throttling, tight shutoff, or both. Control valve packing. Packing is an essential sealing system typically made from deformable materials such as TFE, graphite, asbestos, or Calrace, among others. These materials are chosen for their durability and ability to withstand extreme conditions, including high temperatures and pressures. The packing material usually comes in the form of solid or split rings, which are placed within a packing box. When the packing is compressed, it forms a reliable pressure seal that effectively isolates the fluid inside the valve body from the outside atmosphere, preventing leaks. This compression creates a tight seal around the moving parts, such as a valve stem, ensuring that the system operates safely and efficiently. However, due to regular use, the packing material can degrade over time, so periodic maintenance is crucial to maintain the integrity of the seal. Actuators. Let's now talk about actuators, the muscle behind valve operation in a control system. The actuator is the device that provides the force or power needed to move the valve stem and plug. Think of it as the link between the control signal and the actual movement of the valve, a crucial intermediate component that translates a control signal into mechanical motion. In most industrial applications, the power source used for actuators is compressed air. Why? Because air is not only reliable, but it's also inherently safe to use in hazardous environments, which is a big advantage in industries like oil and gas. Now, in pneumatic actuators, the diaphragm pressure corresponds directly to the pneumatic control signal, typically ranging from 3 to 15 psig. This range represents 0 to 100% of the control signal, allowing for precise modulation of the valve. Let's break down the advantages and disadvantages of two common actuator types: pneumatic diaphragm actuators and pneumatic piston actuators. Pneumatic diaphragm actuators advantages: lowest cost solution, capable of throttling even without a positioner, simple design, inherent fail-safe action, operates on low supply pressure, easily adjustable, easy to maintain. Disadvantages: limited output force capability, bulkier and heavier compared to other types. Pneumatic piston actuators. Advantages: high torque output, compact and lightweight, performs well in high ambient temperatures, fast stroking speeds, offers relatively high actuator stiffness. Disadvantages: fail-safe action requires additional accessories, needs a positioner for accurate throttling, generally more expensive, requires higher supply pressure. Each type of actuator has its own strengths and trade-offs. Choosing the right one depends on the specific needs of the application, whether you need high torque, fast response, or simplicity and fail-safe operation. In the next segment, we'll take a closer look at how positioners enhance actuator performance. Let's take a closer look at electric actuators. Advantages. One of the biggest benefits is their compactness, which makes them ideal for space-constrained installations. They also offer very high stiffness, meaning they resist movement when not actively powered, great for precise positioning. On top of that, they deliver high output capability, making them suitable for operating large valves under significant loads. Disadvantages. However, these benefits come at a higher cost compared to pneumatic or simpler systems. Another key limitation is the lack of inherent fail-safe action. Without a power source or additional battery backup, they can't automatically revert to a safe position. Electric actuators often have a limited duty cycle, meaning they're not suitable for constant operation without overheating. And finally, stroking speed tends to be slower than pneumatic or hydraulic systems, which can be a drawback in fast-acting applications. For applications that demand even more force and control, electro-hydraulic actuators or similar high-performance systems come into play. Advantages: they offer high output capability, making them ideal for large valves and high-pressure systems. High actuator stiffness ensures excellent control, even in dynamic conditions. Their excellent throttling ability allows for smooth and accurate flow control. And they come with fast stroking speeds, perfect for quick response requirements. Disadvantages: as expected, these systems are expensive and come with greater complexity, which can make maintenance more challenging. They also tend to be larger and heavier, which might limit where and how they can be installed. And while they can be designed to fail safe, it usually requires additional accessories to make that happen. Now let's talk about one of the most important parts of a control valve, the actuator. The actuator is the muscle that moves the valve based on the signal it receives. Here, we're looking specifically at spring and diaphragm actuators, which are very commonly used. There are two main actuator movements, linear and rotary, and each can be configured for different fail-safe actions. Let's break it down. 1. Linear spring, diaphragm actuators. In these actuators, the spring and air pressure work against each other. The spring is used to bring the valve to a safe position when air supply is lost. Based on the spring and plug orientation, we get different fail-safe modes. Air to open or fail closed, also called reverse acting. Air pressure pushes the stem down to open the valve, and the spring closes it when air fails. Air to close or fail open, also known as direct acting. Here, air closes the valve, and the spring opens it when air fails. Rotary spring, diaphragm actuators. Now let's look at rotary actuators, often used in valves like butterfly or ball valves. These actuators rotate a shaft instead of moving a stem up or down. Direct action air pressure rotates the shaft to close the valve. Spring returns it open on failure. Reverse action air rotates to open the valve. Spring closes it when air fails. Watch for the direction of shaft rotation, clockwise or counterclockwise, to understand which way the valve opens. So depending on the process safety requirement, you can configure the actuator to either fail open or fail closed. This is a key part of valve sizing and selection, especially in critical operations like steam, fuel gas, or chemical lines. Positioner. In any process control system, precision is key. And when it comes to controlling valves, even the slightest deviation can impact efficiency, safety, and performance. That's where valve positioners come into play. A valve positioner is a device used to accurately position the valve stem based on the signal received from the controller. Think of it like a personal assistant for the valve actuator. It makes sure the valve does exactly what the controller wants. The positioner adjusts the air pressure to the actuator until the valve stem reaches the correct position. It's usually mounted right on top or the side of the actuator and is mechanically linked to the valve stem. This link allows the positioner to constantly compare the actual valve position with the desired one. What does a positioner do exactly? It acts like an intelligent relay between the controller output and the actuator diaphragm. By doing this, it helps overcome real-world issues like hysteresis, friction in the packing box, unbalance from pressure drops across the valve. So instead of relying on air pressure alone, the positioner ensures exact stem positioning, which is essential for precision control. Types of positioners. Pneumatic to pneumatic, where both input and output signals are pneumatic. Electro-hydraulic, where the controller signal is electrical, but the actuator is hydraulic or pneumatic. Why use a positioner? There are many reasons you'd want to install a positioner on your valve system. Here are just a few powerful ones. Improve control resolution for fine adjustments. Compensate for high temperature packing friction. React quickly to process changes. Allow split range control. Help in long distance setups between controller and valve. Support rotary valve seating where friction can be high. Enable wide flow variations, even with minimal travel. Increase reliability when using 4 to 20 mA signals or piston actuators. So, in essence, if your control system demands precision, fast response, and flexibility, a valve positioner is the device that brings it all together. Without it, you're just guessing where the valve is, and in process control, that's a risk you don't want to take. Now let's quickly break down the principle of operation of a valve positioner. The positioner is mechanically linked to the valve stem. This mechanical connection allows the positioner to always know the actual stem position. That's critical. Then comes the controller. It sends out a signal, usually a pneumatic 3 to 15 psi or an electronic 4 to 20 mA signal, telling the valve where it should be. The positioner compares the actual valve position to the desired position from the controller. If there's any mismatch, the positioner acts like a smart middleman. It adjusts the air pressure to the actuator using its own separate air supply until the valve stem is exactly where it should be. This precise feedback loop makes the control system highly accurate, responsive, and reliable, especially in complex process conditions. Now let's talk about some essential control valve accessories that help ensure precise, safe, and reliable operation in process control systems. First up is the solenoid valve. This is an electrically operated valve that controls the air supply to the actuator. It's widely used for on-off applications and emergency shutdowns. When you send an electrical signal, the solenoid opens or closes to allow or block air, simple and effective. Next, we have the air filter regulator, or AFR. This component filters out moisture, oil, and dust from the instrument air and regulates the pressure to a stable level, usually around 20 to 30 psi. Clean, dry, and stable air is crucial for keeping your actuator healthy. Moving on to the lockup valve. This one's all about safety. If the instrument air supply fails, the lockup valve holds the actuator in its last position, preventing unwanted or unsafe valve movement. Now, when we deal with large actuators that require fast response, we use a volume booster. Think of it as a pneumatic amplifier. It quickly fills or vents air to help the actuator respond rapidly to changes from the positioner. Supporting that is the volume tank. It stores pressurized air to meet sudden demands during quick valve movements. This is particularly useful in emergency operations or fast-acting control loops. Let's not forget the limit switch. This small but important accessory tells the control system whether the valve is open or closed. It's widely used for feedback and interlocks in automated systems. And finally, the hand wheel. This provides a manual override. In case of air or power failure, operators can still manually open or close the valve for maintenance or emergencies. Together, these accessories enhance the functionality, reliability, and responsiveness of control valves in any industrial setting. Let's now get into the core of valve sizing, the flow curve. Refer to the sizing equation for liquid. Refer to the sizing equation for gas or vapor. Cavitation. Now let's talk about an important and potentially damaging phenomenon in liquid flow systems, cavitation. Cavitation occurs when the pressure of a liquid falls below its vapor pressure at a certain point in the valve. This causes vapor bubbles to form. Then, as the fluid continues downstream and pressure increases again, these vapor bubbles collapse violently, and that's cavitation. This rapid formation and collapse of vapor bubbles causes intense localized shock waves. Over time, this leads to pitting, vibration, noise, and even severe damage to valve internals and downstream piping. Cavitation can often be recognized by a distinct rattling or cracking noise. It actually sounds like stones or gravel passing through the valve. While it's possible to predict cavitation using pressure conditions and the valve recovery factor, Florida, it's important to understand that the actual damage depends on the energy being dissipated, flashing. Let's now look at flashing, another critical phenomenon in liquid flow control, often confused with cavitation, but quite different in behavior and impact. Flashing occurs when the pressure of a liquid falls below its vapor pressure and stays there. As a result, the liquid doesn't just form bubbles that collapse later. Instead, it turns into a mixture of liquid and vapor that continues to flow downstream together. This is known as two-phase flow, a combination of vapor and liquid, and it can be very destructive. Why? Because high-speed liquid droplets traveling in this mixed flow can cause severe erosion on valve internals and downstream piping. The constant impact at high velocity leads to metal loss, scoring, and material fatigue. Unlike cavitation, where the vapor bubbles collapse back into liquid, flashing is permanent vapor formation within the process line, and it's much harder to eliminate once it begins. And that wraps up our deep dive into control valves, from the basics and classifications to flow characteristics, leakage standards, and real-world applications. Control valves may look simple on the outside, but as you've seen, their selection, sizing, and performance are all rooted in precision engineering. Understanding these fundamentals is the first step in becoming a smarter, more confident instrumentation professional. If you found this video helpful, don't forget to like, share, and subscribe to Instru Nexus, your hub for all things instrumentation and control. Drop your questions or suggestions in the comments. I'd love to hear from you and cover more topics that matter to you. Thanks for watching, and until next time, stay curious.